This video will be dealing with Chapter 8, which is on estimation. Estimation is where you want to find the value of a parameter from a statistic. So you're actually going to estimate what you think the value of a parameter is from a statistic that you can get from a sample. So the first section is about basics of confidence intervals. A confidence interval is an interval of values around a point estimator. In other words, it gives you a range of values for what that point estimator could be. And what a point estimator is basically what we've been dealing with already, a statistic. So if you're interested in the mean, mu, then your point estimator is x bar, the sample mean. If you're interested in the population parameter p, then your point estimator is p hat, because we can't use a Greek letter for p. If you happen to want to know what the standard deviation is, then your point estimator is the sample standard deviation. So you can see we can look at the population parameters, which are these here, and the sample statistics. And there are a lot of other ones we can do besides these, but these are the sample statistics that go with those population parameters. Again, they're called point estimators because they're a single point out there in space. And what we're going to do is give you an interval instead. In general, the population parameter is a Greek letter theta, and the sample statistic is a theta with a little hat on it. So we call it theta hat. All right, so moving on. The general form of a confidence interval is that the theta, the thing you want to estimate, is between theta hat minus some value, e, and theta hat plus some value, e. So you basically are capturing the theta, that parameter you want to know, in between two values that have to do with adding and subtracting a single value from your statistic value. E is known as the margin of error, and so it actually involves not just your sample standard deviation, but it also involves your sample size and basically what we call an error term, a value that kind of relates probabilities to it. And we get those values from looking up on finding probabilities with either a z-curve or a t-curve. So let's just suppose that n equals 7 and your standard deviation is 1 and your x bar is 12. Thus, a point estimator for mean, mu, is 12. N equals 7 is low, so I'm not real confident about this above statement because n is only 7. S equals 1 is low, so that raises our confidence about the above statement. If you don't have a very high standard deviation, it means your data wasn't very spread out in the first place. So you're pretty confident that your x bar was 12 is a reasonable value for mu, but you're not perfect. So what we do is we create a confidence interval that brings in a confidence level of how confident we are about our answer and also how sure we are, kind of including that sample size and that standard deviation into it. And we basically call these a level of confidence, which we call C. C can be lots of different numbers. Usually we see 0.8 or 80%, 0.9 or 90%, 0.95 or 95%, 0.98 or 98%, or 0.99, 99%. We usually see 0.9, 0.95, and 0.99, but I have seen lots of other ones. So let's just look a little bit at some relationship here. If we fix our sample size as a certain number, so I'm going to take a sample of this size. As I get more and more confident about my answer, the width of my confidence interval increases. So you can kind of think about it as the best way I can think of it is the ring toss game. If you have a post out here in space and you're trying to throw a ring around it, I can get really confident that I'm going to get my post around that ring if my ring around that post, if my ring is really, really big. But if my ring gets smaller and smaller and smaller, I'm going to be less confident I get the answer. So if I get more and more confident that I'm going to get my ring around that post, I have to have a bigger ring to throw. And so that's why we say that as your confidence level increases, as you get more and more confident about your answer, the width of your confidence interval actually increases. Now, if we increase the confidence level, then, like I said, that width gets wider and wider and wider. So now let's say we do it the other way, by the way. If you get less confident, then you can be a smaller and smaller interval, because your ring, you can actually be less confident that you get the little tiny rings around it, but you're more confident you get the big rings. So kind of think of it as your parameter is some post out there in space, and you're trying to throw a ring around it. The bigger your ring is, the wider your interval, in other words, the more confident you're going to get it. The smaller your ring, the tighter your interval is, the less confident you're going to get. If you want to be more confident and also get a smaller interval, then we actually could fix our confidence level to be a certain value. So we'd fix C. And then as I do it more often and get more and more practice, I'm going to get better and better and better at getting my ring around that post out there in space. So that means that if I increase N, get more and more trials, more and more values, I'm going to get more and more accuracy. So my width will actually get smaller. So that's kind of what we can say happening. Statistically, the interpretation of a confidence interval is that there's a certain percentage chance, or what we call C% chance, that that interval, whatever interval you come up with, contains the true value of your parameter. So as an example, if I, again, throwing that ring around, my small little tiny ring, I'm like 90% sure I'm going to get that small ring around my post. My post is out there in space, and I'm 90% chance I'm going to get my interval around that post. As I get more and more confident, again, my interval is going to get bigger and bigger, but I still, let's say I have a 99% chance I'm going to get my ring around that post, because sometimes I still won't get it even though I have a pretty good ring. So the idea is that you're confident about how sure you are that your interval is correct. You're not confident that the value's there. That value's sitting out there in space somewhere. You're confident that you can capture it. So you're confident, you're 95% confident or 99% confident, whatever the confidence level is, that you're going to capture that parameter, and it has nothing to do with that parameter moving around. So that's your statistical interpretation. Your real-world interpretation involves you basically telling the world what the value of the parameter is. So if you are looking for the proportion of people who get pregnant using in vitro fertilization, let's say the proportion of people who get pregnant are between 20 and 35% of the people get pregnant, then you would actually, if you were an in vitro clinic, you would tell people, hey, 20 to 35% of people get pregnant using this method. So it's just letting people know what the values you got. So that's what real world interpretation is. Just like with the hypothesis testing, confidence intervals have to do with having a, we won't get too much into this, this page here. This page here talks about your relationship between your confidence level and alpha. So if you know what your alpha level is from your hypothesis test, you can calculate your confidence interval by doing 1 minus alpha. If you are not equal to HA, if you're greater than or less than, then your confidence level is 1 minus 2 times alpha. So if you know what your alpha is, you can find your confidence level. So that just gives you kind of an idea. Again, confidence intervals, just like hypothesis tests, depend on what you are trying to estimate. So if you're trying to do a confidence interval for the proportion P, then again, you would state your random variable and parameters, just like we did for hypothesis test. You'd state and check your assumptions, just like we did for hypothesis test, and they are the exact same assumptions that you did for a hypothesis test on the proportion. So once you've done the hypothesis test, if you then do a confidence interval, you've already tested and stated your assumptions, so you don't need to do that again. Your calculations are exactly the same. you would actually, I'm going to ignore this because you're not doing this, but you would actually do prop.test, put in your X value, which is how many successes you saw, put in your N value, which is how many people you tested, and then you do conf.lev level. So it's basically confidence level, but conf.level equals C, and you put in whatever C value you're going to have. So if you're doing a 95% confidence level, you type in 0.95. If you're doing a 99%, you type in 0.99. So you always type your C in as a decimal. If you're doing a confidence interval for the mean, mu, then again, you state your random variable parameters in words, just like we did for the hypothesis test. You state and check the exact same assumptions we did for the hypothesis test. And then again, we're going to skip some of this, but your calculations on R would again be t.test. You type in your variable and you type in your conf.level equals C, and again, put the C in as a decimal. So that's how we do confidence levels. That's kind of the plane of how they look.